So it's not all that.
Right.
All right, so we talked about equilibrium. So we have an equilibrium constant. So let's take a look at a generic reaction. A plus 2B going to C plus 3B. All right? What's the equilibrium constant? Form of the equilibrium constant going to be?
C times
Constant,
D,
yeah.
to D
Third power.
and then
Over the
A,
others. A raised to the first power,
B raised.
B raised to the second power. Equilibrium constants always look like that. They always have that same form.
So it's the products over the reactants with the
Yes.
coefficients. as
Always
the
product
exponents.
over reactant. Now,
It has nothing to do with orders, obviously, it's just so you know.
well, in actuality, it does have to do with order, because this represents the steps, the elementary steps of a forward reaction and a backwards reaction. The forward reaction is A plus 2B going to C plus 2D, and associated with this is an equilibrium constant and another equilibrium constant. And it turns out that you can rearrange these and get another constant out that has this form. Where this would represent the element. We have two reactions that are happening at the same rate. The constants are different, but the rate is the same.
But like, I mean, that wouldn't necessarily be 3 and 1, it wouldn't be a fourth order reaction.
No, yeah, we wouldn't consider ourselves with the order.
Yeah.
If we were just talking rates, if this was just the rate, yes, this would be a fourth order,
Yeah.
molecularity wise or whatever. But we're not, exactly. So another nice thing about equilibrium, they're constants. All right? These are constant. At a given temperature, K is a constant, and that means that these concentrations are fixed by the reaction concentration. So let's just say that this is equal to, at equilibrium, we find that this concentration is 0.1 molar, this concentration is 0.3 molar, this concentration is 0.4 molar, and this concentration is 0.3 molar. This is at equilibrium. We see these concentrations. So far, so good? What's the equilibrium constant? What's the value of the equilibrium constant? I'm sorry, what was that?
Plug and shove.
Plug and chug, exactly. If we know these values at equilibrium, it's quite trivial. We just plug in the values we know. 0.3 molar raised to its respective power, 0.1 molar raised to its respective power. All of that in line going to 0.3 molar raised to its power and 0.4 molar squared. Now we can actually leave out the units because equilibrium constants are actually unitless because really we're measuring something else.
Why do they have to be brackets?
It's just the brackets that represent. This is our standard symbol for concentration. It's usually used in molarity. So it doesn't have to be brackets. You could use partial pressures. And I hate writing partial pressures though because it's just so messy. You have to.
Why couldn't you just do it the way you did?
Because you should write this down. That way you don't have to think about it. This should be written down.
Oh no, I'm saying that's fine, but you didn't make brackets over here. You just made little parentheses.
Yeah, well, because at this point it's all math. All right. So give me a number.
0.6 to negative 4.
1.6 times 10 to the negative fourth. All right, beautiful. Now, let's look at another situation. What if, instead, we had the following concentrations? Rather than being at equilibrium, let's look at a test case. What if the concentration of A was equal to 0.25 molar? The concentration of B...
That number is actually wrong.
What number am I looking at?
Okay, it's 3.3 times 10 to the negative 30.
Times 10 to the negative 30, yeah. All right. A is equal to 0.25, B is equal to 0.41, C is equal to 0.33, and D is equal to 0.09. So instead of giving us equilibrium concentrations, they say that we're going to mix these things together. Is the system at equilibrium? How do we know if it's at equilibrium?
If you do that equation and concentration of V times 10 negative.
Go ahead, Pete, say it again.
If the constant is the same as the equilibrium constant, it's in equilibrium.
If it's at equilibrium, the concentrations, when you plug them into the equilibrium expression, will give you the value of the equilibrium constant. If it doesn't equal that value, it's not the same. So what we do is we do a little math trick called the reaction quotient. We use the exact same form of the equilibrium constant, and we say, okay, we're just going to put this query, the reaction quotient. We say, okay, Q has exactly the same form of the equilibrium constant. If Q equals K, then yay, we're at equilibrium. All right, everybody's happy. So, plug the values in and see if we're at equilibrium. In a problem, basically they're saying, they will literally ask you this question: is the system at equilibrium? That's that.
And they give you the equilibrium constant?
Yeah, they would, or they would say, or they do what we did. Here it is at equilibrium. Let's change them and say, and for that we use the reaction quotient.
Right. As far as like introduction to equilibrium, these are the kind of problems that work.
5.72 times 10 to the negative 30.
So what you've got now as a reaction quotient is the following: 5.7 times 10 to the minus
So
30.
they're not in equilibrium.
It's not at equilibrium. Now here's the hard part. What direction does the reaction have to go to re-attain equilibrium? All right, now I'll show you the easy way. All right. Remember what K is. K is equal to the products over the reactants, approximately.
So the bigger number, that means there's more products.
Right.
Yeah. So the reaction has, see this
Reverse.
number, because Q is larger than K, the reaction has to go backwards. So what will happen is C and D will be consumed, making more B and A. And in the process, re-attain equilibrium. This is Le Chatelier's principle. Right? So we can actually make these sort of at equilibrium, Q is equal to K, and then if Q was larger than K, then the reaction would go backwards. And if Q was smaller than K, the reaction would go forwards. Think about this. If you have a reaction, you just start with nothing but product, starting material. Empty vessel, you load A and B into it, there's no C and D. This effectively is very, 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 very small as a reaction quotient. The reaction will sort of dominate to get to equilibrium, moving forward. Same the other way, moving backwards if it was all products. Le Chatelier's principle says when you perturb an equilibrium, it tries to re-attain equilibrium. That means that if we take away one of these components, it tries to be replaced. If we add one of the components, it tries to be eliminated. And the reaction will move in the correct direction to minimize that irritation. So
the equilibrium shifts.
the equilibrium shifts, but it doesn't really shift. It's more like it's out of equilibrium, and so it shifts in a way to re-attain equilibrium. Once it's at equilibrium, things are golden. It's not going to shift anywhere. Pete.
So, if somehow you remove some of the material or something, like obviously it can get the concentration.
Here's
The ratio would be the same, like the constant would be the same. Is that what would?
the constant never changes. The constant is a fundamental fact of the chemical equation. It says that this reaction wants this balance.
But if you add a bunch of something else, doesn't it change?
It perturbs the equilibrium. And then it tries to the classic example of this is a reaction that is being run, and you have A plus B going to C plus H2O. The H2O, you do it at high temperatures, the H2O comes off as H2O gas, and you trap it as water, and you remove it from the mixture. And so you trap it. It's a classic organic experiment. It's called azeotropic distillation, where you separate out the water from the reaction mixture. So you have a reaction mixture here, A plus B going to C plus water. And you trap the water here. As the water is produced, this gets effectively removed, forcing the chemical reaction to try to re-attain equilibrium, making more water. But you're continuously removing it, forcing the reaction this way, this way, this way. Eventually, you run out of A and B, and you're left with nothing but C. It's a nice trick. All right. So that's reaction quotient in a nutshell. If you ever ask you, is the system at equilibrium, it's just like approaching it from the equilibrium standpoint. Using the equilibrium equation or the form of the equilibrium equation in the reaction quotient. The reaction quotient will tell us which direction the reaction will proceed as well. Now, qualitatively, we can say, well, if we change one of these components, if we're adding stuff to the products, it's going to move backwards. If we're taking away products, it'll move forwards. If you're adding stuff to the reactants, it'll move forward. If you're adding stuff to taking the reactants away, it'll move backwards. So that's a quick and dirty way to analyze it. But there are more mathematical ways to do it as well, but we're just going to sort of skip that for now. The next portion of this is what we're going to do. We're going to start breaking up the algebra and looking at the change, plus x, minus x, etc. So,